Hello everyone, this is Abhinav Ganluri, and this video is as part of a research paper presentation for COSC 5302 Advanced Operating Systems, and the topic that I have chosen for this presentation is Cassandra, its principles and applications. This paper was originally published by Dietrich Featherston, and he's one of the professors at the Department of Computer Science at University of Illinois. Okay, let's get started. This is the overview, and we're going to look at all these topics through this presentation. We're going to introduce Cassandra. We're going to talk about CAP theorem and PACE-LC, which is a model that is helpful for NoSQL services like Cassandra, and we're going to talk about the data model that Cassandra is built on. We're going to look at the distributed hash tables, which is a fundamental principle in distributed systems, and we're going to talk about architecture that Cassandra uses. We're going to talk about, when we say architecture, we're going to talk about the read and write operations of Cassandra, and the elastic storage, like the scalability of Cassandra, and the consistency. And we're gonna talk about client access, like how the client is being able to interact with a decentralized system like Cassandra, and we're gonna see a case study that is being described in the paper, which is a modeling airline activity, and finally we're gonna look at the conclusions that are drawn from this paper. Okay, this is the picture that I have taken from Google. So when you see this picture, you see that the most of the companies that are here are big companies that deal with huge amounts of data, like millions of customers of data on daily basis. So why do you think they use Cassandra? Because if you use traditional relational databases like MySQL or Oracle or SQL Server, it is not possible to retrieve data of millions of customers with ease. So basically it's going to take forever if you want to query the results. So that's the main reason why these big companies switch to using Cassandra. Okay, we can see the introduction of Cassandra. So basically it is one of the most popular NoSQL databases, and when we say that it's NoSQL, we meant to say that it's unlike a relational model, unlike traditional relational databases. So like traditional relational databases, they store schema in a normalized form, and we're gonna need to be using joins, constraints, primary keys, indexes, and many other things, and a lot of tunable queries to get faster results. So we're saying NoSQL as anti-relational because it doesn't guarantee any ACID properties. Basically Cassandra is a distributed key value store, and it is based on a key and values. So the queries are basically based on keys. And Cassandra is said to be highly scalable, and is said to have no single point of failure, unlike the relational database systems. And it is said to be fault tolerant, and has showed pretty much very fast writes and read operations. And the most important thing is it is said to be highly available. That is because Cassandra enables this high-level system availability by compromising data consistency, but also it allows the client to tune the extent to this trade-off. So basically it allows certain trade-offs to choose between consistency or availability. And also the Cassandra is its core design is based on Google's Big Table and Amazon's Dynamo. Google's Big Table is one of the consistent model, and Dynamo from Amazon is also a consistent model, but it is client tunable, and these two have introduced some of the new concepts in the database terminology and new techniques, and Cassandra basically draws these techniques from these two papers, and it is basically developed by Facebook as a data platform to build many of their social services like Inbox, which is used for its messenger applications, and later Apache software accepted it as a major project, and the Cassandra is said to achieve order of 1 complexity over the lookup table. So we're going to look at the CAP theorem, and later we're going to look at the refined model of the CAP theorem, which is called PACE-LC. So we already said that Cassandra is a NoSQL database. Like it is one of the many new data storage systems which are moving to NoSQL. So NoSQL is basically a term often used to describe a class of non-relational databases that scale horizontally to very large data sets, but they do not in general make any ACID guarantees. When we say ACID guarantees, it's like atomicity, consistency, isolation, and durability. These are some of the properties that relational database models exhibit, and NoSQL doesn't care about it. So this CAP theorem was first conceived by Eric Brewer, and it was later formalized into a theorem by Nancy Lynch. So this theorem has basically become a useful model for describing this fundamental behavior of this NoSQL systems. So what is this theorem? Basically, this theorem states that for any distributed system, it is impossible to be consistent and to be available and to be partition tolerant at the same time. So when we talk about consistency, availability, and partition tolerance, so a distributed system can never have all these three states at a time. It can satisfy any two of the states at a time, but it cannot have all the three. So when you say consistency, it means that all copies of the data in the system appear to be same and identical to the outside user at all times. And when you talk availability, it means that even when there is a node failure in the system continues to operate as a whole. Like when you say a failure, the hard drive in a server may fail, so that is considered as one of the failure, or when there is a broken link or a router in a cluster. And partition tolerance. Partition tolerance basically requires that the system continues to operate in spite of arbitrary message loss. Such an event may be caused by something like a crashed router or a broken network link, basically which prevents communication between groups of nodes. So basically this is the CAP theorem, and depending upon the user's requirement, the Cassandra the user of Cassandra can opt for either availability or partition tolerance or consistency. So basically the client is given a choice here to choose how his application is going to work. So this CAP theorem is one of the popular models for understanding the necessary trade-offs that are being done in distributed data systems. But however, there are some underlying assumptions in CAP theorem which are observed by Daniel Abadi. He's from Yale University, same as Department of Computer Science, and he proposed a refined model for the CAP theorem. So basically he clarifies trade-offs buried within the CAP theorem, and this is the figure that he used to describe the trade-offs buried within the CAP theorem. So basically what he states is that when a system experiences partitioning P, then it tends to require that trade-offs be made between either availability A and consistency, or else under normal operations it must make trade-offs between consistency C and latency L. So basically Cassandra must sacrifice to remain available. This is basically because the right to durability is basically impossible when a replica is present on a failed node. The reasons behind these trade-offs are discussed in detail in further slides. In this slide, we're going to discuss about the data model that Cassandra is built on. So these are the terminologies that we will be looking up. So someone who is familiar with relational databases can relate all this terminology, and they can easily understand this. So we have something called key space, and we have something called column family, and also something called row keys, column value. Unlike the traditional relational databases where you use a standard query language called structured query language, you use SQL queries with a lot of constraints and joining criteria to get the results. Whereas in Cassandra, user is allowed to search for the data or to be queried only by its key. So basically the data modeler must choose keys that can be derived or discovered easily, and the referential integrity has to be maintained. So basically Cassandra adopted some of the techniques from Google's big table, and it has adopted all these abstractions of Google's big table and implemented this. So what is a key space? So basically a key space is the top level unit of information in Cassandra. So basically this column family which you can see here, it is subordinate to only one exact key space. So what does it say here? Key space is container for the application data, similar to a schema, something like a schema in a relational database. And what is a column family? A column family is basically It's one of the unit of abstraction containing keyed rows, which in turn have column keys and column values. So column key is something like uniquely identifiable in a row, and a column value basically stores one value or a collection of values. And this is the row key. Row key basically uniquely identifies a row in a column family as a whole. And also we have something called a super column. Super columns basically group together the columns with a common name, and they are useful for modeling complex data types such as addresses. So one more thing that we need to take care of here is that all column names and values must be stored as bytes of unlimited size, or basically something like 64-bit long integer types or UTF-8 strings, etc. So this is basically the data model that Cassandra uses. And we're going to talk about the distributed hash tables in the next slide. So a distributed hash table is basically a fundamental principle of the distributed systems, and it is basically a strategy for decentralized key data storage, which offers something like get and put operations. You get a value by giving the input key, and you do put operation by giving the inputs key and value. When we recall something like Napster, which maintained a listing file locations on a central server, there's always some problem with this approach, because the central server has the reference data to the locations that user wants to search for the file he's looking for. There's always a possibility for bottlenecks at that node. I mean, there's a large amount of strain in terms of processing power and bandwidth at that node, and there's a chance of for the central node to be appeared as unavailable. So DHTs offer a scalable alternative to this central server lookup. So what they do is basically they offer they look up and store they distribute lookup and storage over a large number of nodes, which we call as peers, without any coordination of a central server. So what we use here is basically key-based routing. Any read or write operation on a distributed hash table must locate the node containing information about that key. So this is basically done through key-based routing. So what happens is each node participating in a DHT contains a range of keys stored along with information about the range of keys available at 0 or more other nodes in the system. So when a node is contacted for information regarding a key, it will forward that request to the immediate next nearest node according to the lookup table that it has formed. So basically, you get very fewer hops if the more information each node maintains about its neighbors. So we already know that many DHT systems like CORD exhibit order of log n, and whereas Cassandra's implementation of DHT achieves order of 1 lookup complexity. This is because it uses something like gossip architecture, which is adapted from Google's Big Table. This basically make sure that each node is eventually has the state information of every other node that is available in the cluster. So when we talk about the DHT implementation in Cassandra, basically unlike other DHT implementations, all the nodes in this cluster are assumed to be in a logical ring structure. So basically the servers are numbered like sequentially around the ring, with the highest number connecting back to the lowest number. So each server in the Cassandra is assigned a unique token. We're going to discuss that in the next slide. So we already told that the nodes in Cassandra are arranged in the form of a ring. So each server is assigned a unique token which represents the range keys for which it will be responsible for. So the value of the token may be any integer. It may be an integer or a sequence of bytes, or a 64-bit integer, something like that. So however, they are converted into the token domain using a consistent hashing algorithm. So when we're implementing a DHT, it is obvious that we're using some hash function, and in this case Cassandra uses MD5 hashing as a default algorithm. If a client or a user wants to use any other hashing algorithm for a number of reasons, they can go ahead and use it. It all depends on your application. So basically, as a result of using this MD5 hashing algorithm, Cassandra achieves even distribution of data and processing responsibilities within the cluster. This is basically due to the domain and range characteristics of MD5 algorithm. So the paper basically says that the load balancing is achieved in Cassandra due to the even distribution of data and the processing responsibilities. Okay, we're going to talk about the architecture of Cassandra in this slide. So firstly, we're going to look at the anatomy of writes. So to the end user, all the nodes in the Cassandra cluster appear to be similar, that is identical. So what does it mean? Like each node is responsible for a subset of the data within the system. So obviously each node is capable of servicing any request that is being issued by the user, whether to read from the key or to write to a particular key. So basically such requests are proxied to appropriate node by checking the key against the local replicas of the token table. So what it does is, once a write request reaches the appropriate node, it is immediately returned to commit log. Commit log is basically an append only and crash recovery file in the durable storage. The only input or output for which a client is basically blocked is for this append operation only. So a write request will not return a response until that write is durable in the commit log, unless you specify a consistency level of 0. All these consistency levels will be discussed in the next coming slides. Okay, there's one more thing called mem table, which is an in-memory data structure adapted from Google's big table paper. So So this mem table is updated with these write operations. So once this mem table reaches a certain size, it is periodically flushed to durable storage, something known as a SS table. This has also been discussed in Google's big table paper. We're not going to discuss that in detail here. Okay, the next thing that we're going to look at is the anatomy of reads. So when compared to writes, the read operations are much more intensive, and they typically have higher latency. So basically the reads for a key at one of the replica nodes will first search the memory cache, which is called mem cache. Along with this, any SS tables that have this information is also searched for. So because the constituent columns for a key may be distributed among multiple SS tables, and also each SS table has an index to help locate these columns. So basically, when you have more SS tables, then we have more number of keys stored at a node. And even these SS tables are periodically consolidated to keep read latency under control. Okay, the next thing that we're going to look at in the architecture section is replication. So the one most important concern when dealing with a distributed system is that what happens when a node fails, or what happens when a link or router fails. So Cassandra storage engine implements what we earlier seen as a MD5 keyed distributed hash table. So basically it evenly distributes data across the cluster. So to allow the keys to be read and written even when a node is failed, what Cassandra does is that it will keep some n copies distributed within the cluster. So basically n here it can be termed as a replication factor, and is basically user configurable. So basically each node keeps a listing of n-1 alternate servers where it will maintain additional copies of the data. So that is how the replication is done. This paper provides basically two strategies in determining which node should actually hold the token. So each strategy here is basically provided both with logical topology, which we call as token ring ordering, and physical layout, which is something like using IP addresses of the cluster. So for each token in the ring, the replication strategy returns n-1 alternative endpoints always. So what are the two strategies that the paper has described here? So one is that rack unaware. So it is basically a default strategy used by Cassandra, and what it does is it basically ignores the physical cluster topology. That is, it ignores the token ring ordering, and it returns the endpoints of the next n-1 nodes in the token ring by opting the primary node at the beginning. So that's rack unaware, and rack aware strategy is something which attempts to improve availability by strategically placing replicas in different racks and data centers. That is, basically we use different racks and different data centers to store this data. So even in case of a node failure or a router failure, you don't need to depend always on a single central server because the data is replicated here. So basically this design allows the system to continue operating in spite of rack or whole data center being unavailable. So nodes are assumed to be in different data centers if the second octet of their IPs differ and if the third octet differs, then they are said to be in different racks. So that is how the distinction is being made here. So just like rack anywhere, it also attempts to find a single node in a separate data center, another one on a different rack, and the same data center in the remaining n-1 endpoints using the rack anywhere technology. So that's pretty much about replication of data in Cassandra. So the next thing we're going to talk about is consistency in Cassandra. So starting from the presentation, we always mention that Cassandra is highly consistent and highly available. So how does this consistency is achieved? So the main reason it is said to be consistent and highly available is because it allows the user to make trade-offs between consistency and latency. So basically a client or a user cannot have both at the same time. So clients can basically specify a desired consistency level of a 0, a 1, a quorum, all or any for any operations of its users. So this is the facts about the consistency levels during write operations and during read operations. So a consistency level of 0 indicates that basically a write should be processed completely asynchronously to the client. It means that it doesn't give any guarantee to the consistency, but it offers pretty much a lowest possible latency. And a consistency level of 1 means that the write request won't return until at least one server where the key is stored has returned the new data to its commit log. So if no member of the replica group for applicable token is available, then obviously the write fails. So basically in the consistency level of any one replica including hinted handoff is a return. And a consistency level of 1 is achieved with one replication, that is with one node and a read repair in background. And a quorum level. A quorum requires that we need n/2 plus 1 servers or n/2 plus 1 replicas must have the durable copies. So where n is, as we already said, it's the replication factor. So local quorum means that we need to have n/2 plus 1 replicas in the local data center, and each quorum means that we need to have n/2 plus 1 replicas in each data center. So consistency level of all means we need to have all the replication available, like it can be taken as n as a replication factor. And below is the consistency level for read operations. For consistency level of 0 we don't have anything, so there's no use of that. And for consistency level of any, we need to make sure that we need to use 1 instead of using any. So and similar to that of consistency level at the write operations, the read operations also have the quorum and local quorum and each quorum. So the quorum has n by 2 plus 1 replicas, and the local quorum has n by 2 plus 1 replicas, which is obviously at the local data center, and each quorum has n by 2 plus 1 replicas in each data center. Okay, that's pretty much about consistency in the architecture of the Cassandra. So in this way, basically a balance between consistency and latency is achieved, and that's the main reason why Cassandra is said to be highly available and consistent. So in the next slide, we're going to talk about the next architecture feature, which is isolation and atomicity. So when we already said that NoSQL doesn't carry any ACID properties, unlike the traditional relational database systems. So there is no way to achieve isolation from other clients basically working on the same data as that of the same data that you're working. So basically, if there are two clients working on the same data, you cannot achieve isolation. So but some atomicity is offered, but it is always in a limited scope. So so factors such as atomicity of operations and isolation from other client updates can be critical in many cases, and they're often encapsulated within a transaction construct for relational databases. So Cassandra guarantees a read or write for a key within a single column family or always atomic. So it guarantees that, and it also guarantees that batch updates within a column family for multiple keys which are not guaranteed. And basically the application designers need to look out for these properties in designing their applications. If they want their application to guarantee the ACID properties, then probably it's not a good idea for them to use the Cassandra architecture. In some cases, some of the application designers may choose to put some subset of data that can guarantee the ACID properties, and using traditional relational database, and the rest of the data can be residing on the data store, something like Cassandra. So that can be possible. Okay, that's all about the architecture of the Cassandra. And okay, we're gonna look at the storage properties of the Cassandra. So we always said that Cassandra is highly available, and it can scale to larger data sets. So how do you think Cassandra allows this? So it basically allows scaling to arbitrarily large data sets. So unlike Cassandra, like in a traditional relational database, if you want to scale it for large data sets, all you need to do is you need to have powerful servers, or you need to purchase some powerful hardware, and you need to have a large storage requirements, something like that. So basically hardware requirements and costs, they scale linearly with the storage requirements. So what Cassandra does is it allows itself to grow by introducing new nodes into its cluster, so that the data can be replicated among the nodes within the cluster. This is something basically referred as horizontal versus vertical scaling, and the process of introducing a new node into a Cassandra cluster is referred to as a bootstrapping. So if you consider this diagram like T0 to Tn minus 1, these are the nodes that are in the cluster, which are assumed to be in a virtual ring, and the bootstrapping is basically done in or accomplished in two ways. So the one way is that we need to configure the node to bootstrap itself to a particular token which dictates its placement within the ring. And the other approach is that cluster selects a token dictating the node's placement in the ring, unlike the other way. So basically this figure here shows that a new node Tn dash, this is a new node here, a new node Tn dash being bootstrapped to a token between Tn minus 1 and Tn. So basically the approximate fraction of data that will be migrated from node Tn to Tn minus 1. No, so I'm sorry, from node Tn to Tn dash can be calculated using this equation. This is the equation that has been described in the paper. That's been calculated as a Tn dash minus Tn minus 1 divided to the Tn minus 1. So basically this calculation can be used in selecting a token value that achieves specific load balancing goals within the cluster. Let's say, for example, if a particular node has a limited storage or bandwidth or processing capabilities, so it makes sense that a very small amount of responsibilities are given to it. So while the second approach is something technically like an election in a distributed system terminology, basically nodes are not contacted in very ad hoc way to initiate the election. But the new node makes this decision based on storage load, data gossip from the other nodes. So basically it adopts the gossip protocol that's been described in the Google Big Data paper. So the next thing that we're going to talk about is the client access. So we're gonna see how the client interaction is done with Cassandra. Basically, it can be a challenging thing. So because it can be challenging because since it's implemented in Java, but it doesn't have any native Java application programming interface for communicating from a different address. So one of the most obvious problems for the client basically to decide is to decide on which host it will send requests to. So as each node is capable of responding to any client request in Cassandra, it becomes a problem here. So but choosing a node with a replica of the data to be read or written will result in reduced communication overhead between nodes. So what Cassandra does is basically instead it implements services using something called Thrift API. So what basically it does is each node in the Cassandra starts a Thrift server exposing all its services for interacting with the data for the client. and Hector is basically said to be a native Java client for Cassandra, and it is one of the top layer of the Thrift API. Also, other than the Thrift API, also it supports many other client languages. So it supports something like Java, Ruby, Python, and Erlang. So Thrift is basically a framework that includes higher level grammar for defining services, remote objects, and types. And also it uses a code generator just like RPC Gen. It produces client and server steps, and it uses remote method invocations. So it's something like a remote procedure calls. Basically we have 3 modes of client level failover during the Thrift API. So the three modes are one is fail fast, and the other is on fail try one next available, and the other is on fail try all available. So what is a fail fast? So basically it implements a classic behavior of failing a request of the first node contacted is down. So when basically you contact a first node and it is down, so it fails the request of the client. And the second one is on fail try one next available. So if the first contacted node is down, then it attempts to contact one more node in the ring before it gets failed. And the other thing is on fail try all available. So unlike the other two, if it observes a node fail, it will contact all the nodes in the cluster before failing the request. So as of this writing, no client could be found which intelligently routes requests to replica nodes. So basically a truly intelligent client requires up-to-date information regarding replica locations, the token ranges, and the availability status of all the nodes in the cluster. So depending on this application's purpose, it makes sense to distribute a number of clients throughout the cluster with different responsibilities. So this is all about the client interaction in Cassandra. Okay, the next thing that we're going to discuss about is the case study that the author has described in the paper, which is modeling airline activity. This is something unrelated use case because the Cassandra is more appealing to how can we say that? The immediate users of Cassandra is the social networking sites like Facebook, Twitter, and Instagram, Snapchat, something like that. So what author does here is that he takes something unrelated use case. So this is basically a simple study which models airline activity and allows searching of flights from one airport to another with a configurable number of connections, probably like with n number of connections. And for better results, the possibilities of inconsistent data that could arise are ignored here, and also some assumptions are made on changing data. So in order to model this alien activity in a way that allows searching for flights on a given day, we must be careful enough to select a data model for this activity. So all examples described in this context are within a single key space. Remember that we talked about key space, the terminology in the data model of the Cassandra. Basically the key space, which is something like a schema in a relational database. So our each query will contain basically 4 pieces of information. That is a date, a departure airport, arrival airport, and total number of flights allowed, or hops. You can call it as hops. This is because basically we're interested in following a linked list of flights from the departure airport. A lookup is required that easily finds the list of flights departing that airport on a particular given day. So for this reason, obviously we need a column family, as the data model requires one column family to be introduced. And for this purpose, we introduce a flight departure as one of the column family. So for this column family, if given a key of a day and departure airport, it basically provides a listing of flights that are all available on that day departing that airport. So let's say, for example, we want to know the flights that are departing from Washington Reagan Airport on this particular date. So what is the key? The key is here. The key is 2010, and 07 is for July, and 24 is the 20 is for the date, and the DC is the departure airport. So basically this is the key, and this is the map structure that results the flights that are being departed from the Washington Reagan Airport on that particular date, with all the flight numbers. So basically, to model this data structure, we introduce a new column family called flight departure. So basically the departure date and airport, the departure airport, are combined to create a unique key, which we described as here. Also, we'll introduce a separate column family called flight, which contains detailed information regarding flights. This is more of kind of like more in depth. I mean, like in the earlier query, we just got the flight numbers from the departing airport, whereas this flight column family holds more information regarding each flight. Like, for example, if we use this key and search for a particular flight, 1603, which we got the result from here, it has all the details like takeoff time, landing time, the flight number, departure country, the city, airport, and the carrier that it's been flying through, and the arrival of the country, and city and airport. So basically the flight column family holds more details. In addition to these, we can also introduce some new auxiliary columns, something like carrier and airport, for better results for a given flight. And also the information could also be stored as a super columns within a single flight row. So basically such denormalization is a good strategy, especially in Cassandra, because it minimizes bandwidth and protocol overhead between the client the nodes in the cluster, so that it is more available and it is highly consistent. That's the main reason that we're using Cassandra. For this purpose, for this case study, the source data has been taken from one of the resources that's been given the paper, and a small subset of this data is chosen for applying this algorithm. So basically, the source data is expanded from the flight schedules to flight instances, and it is stored in the Cassandra database. So the author of this paper proposes an algorithm which is developed for searching these flights. Basically, he introduces two new procedures called get flights by origin and get flight by ID, which are basically the simple implementations. What that does is, like, they look up the single rows of data using the flight column family and the flight family. So basically, the flight departure and the flight column families are used when provided a key. So the procedures return the results of the flight's information. So running this algorithm through multiple instances and at various overloads, it has been observed that 2-hop flight routes are calculated in just a few seconds, and whereas a single hop flights are calculated in just in under a second or something like that. So that's pretty much very good result as compared to traditional relational database systems, because in traditional RDBMS, all you do is you store all the data in a single table called flight, and you use joins and constraints to get the results. But it gets more tougher to query as it involves a lot of flight information data, because the flight data for day-to-day basis will be higher in reality. So the primary latency over here is the communication overhead. So this is the flight search algorithm that has been discussed in the paper. So this is one of the procedure. That procedure is get flights. So basically, date, departure airport, destination airport, and the number of hops that you want the algorithm to apply for is given to this procedure. So the keys are basically get flights by origin and get flights by ID. So for this key, what you do is you get the airport. You get the airport with this procedure by passing the flight key. So if the arrival airport is same as the departure airport, then we'll print this comment as capture this 1-hop flight, and we'll add this flight to the get flight by ID. And if or else if the hops are greater than 1, then look up flight details from the flight column family. So we get the flight by get flight by ID using the flight key as the input. So this is a recursive process, and for the requested number of hops, this process repeats, and it will return the list of flights flight routes matching the input of the user. Okay, and the recursive portion of the algorithm is this part, which is the procedure traverse of flights, and this is the algorithm for it. So this is the algorithm that's been discussed in the paper. So why is it a big challenge? Why is it a big challenge for something like this to model in a relational database? It's because the first and simple thing is that the data set growth requires multiple nodes, and also the indexes supporting the queries grow larger to support larger data sets. Unlike that relational database, Cassandra uses multiple nodes, and the multiple nodes have data at them. I mean the data is replicated at all the nodes, so it is easier to get results from the nodes. So the main challenge is here that partitioning across additional nodes. So user must pretty much need to depend on mainly on high dependencies on joins, secondary indexes, and constraints like what do you say, like the queries need to be tuned according to the cardinality and robustness of SQL. So that's the main challenge with using a traditional relational database systems. Okay, we came to the conclusions of the paper. So all in total, what are the conclusions that have been derived in the paper? So first thing is that the paper has provided an introduction to Cassandra and its architectural principles, and it has discussed about the data model that it's built on, and its distributed hash table implementation, and how it has achieved order of one complexity lookup or one hop DHT. And also the paper has discussed about Cassandra's model for trading consistency, availability, and latency. And also it has discussed about intelligent replica placement, that is by replicating the data among the nodes in the cluster. And also it has discussed the challenges with the relational databases by demonstrating a case study. So okay, that's pretty much about it, and these are the references that I have used for making this presentation. This is the main paper, Cassandra Principles and Application by Dietrich Featherston, and this is the wiki of Apache software that has the gossip architecture and of the Cassandra, adopted from Google Big Table, and you can find a Thrift API work in this link, and these are some of the YouTube videos that I have referred for this presentation. Okay, thank you for watching.